times x minus this divided by x minus this. Okay, that's the first thing I do. The second thing is, if you plug in, now you have infinity over infinity. We need to check the leading terms. Simplify. Negative 10x. All right. Now leading terms, it's easy to check. On the bottom is x. This gives you a square root of x squared, which is x. This gives you x. So together, it's x. One minus. Now what we put here, we should be careful because we're dealing with negative infinity now. We should put this one into this. But we should put a negative sign here because when this go in, you lose the negative sign. So and the inside is nothing but 1 plus 10 over x. That goes to 0. We finally have, it's already done. So negative 10, 1 minus minus 1. Negative 5. And it's correct. So I would say the key part is the negative sign here. Just be careful. Okay, it's negative infinity. Aaron, what do you have?
2.6, number 23, please.
Oh, that's a lot. Do you have a particular one, or do you want me to go over all of them?
You can just do one of them. That's fine.
Okay. Do you have a preference?
No, not really.
Okay. Yeah. Let's
Did you do the second one?
The second one. All right. Limit. So we have two parts. We just need to find every single one and sum them together using some common sense. Okay. The first one, you can see the top is x, the bottom is x. So together, the first one becomes 9 over 8. This eventually is going to give you 9 over 8. The second one, however, you need to check the leading term. You find the top is 9x squared and the bottom is 11x squared. Because the x squared cancel each other. So together it's going to be, oh, three, no, 3, no, 11, no. Then I think this is the easiest form we can get. Something is wrong. It's 121. Oh, I copied the wrong thing. That's why. 9 over 8. Let's redo this. 2151. The bottom can be divided by 2 and 411. Now from work. Okay, this should be the answer. Mm-hmm. Okay, I don't know what's wrong with me. Clearly, I'm missing a lot. That's the indicator that I'm getting older. So don't have kids. You know, you lose your memory, and now you're not sharp anymore. Let's hope this time it's right. I have a feeling it's wrong. Why do I have this feeling? Okay. Did I copy the right thing? Oh my God.
How did you get 8 plus X? How did you get 8X?
Okay, I'm done. One more time. And then, okay. Like my brain is fried. All right, this time is correct. So that's the answer. The key is still finding the leading terms. And I have to say, probably, if I don't ask you to show the work, you just focus on the term and just throw away the others. Okay. Otherwise, you have to do it the formal way. You have to divide it and use the fact. Other questions from homework? Aaron, do you have more or? Okay. All right, let's continue. 2.7, 2.8, derivative. The first thing we did, we talked about derivatives at x equals a. We have formula 1. And the formula 2. As far as I am concerned, we will do either, whichever way you prefer. Okay, they gave you the same answer. We say this tells you the changing rate. Meanwhile, this is the slope of the tangent line. Yeah, speaking of which, yesterday during the office hour, I received a really interesting question. That is, why is the line called secant line? And why is it called tangent line? So we actually Googled. Secant line in Latin means cut. Okay, so secant line is actually the cut line. And you can guess what tangent means in Latin. It means touch. So the cut line, the touch line. Pretty awesome. Okay. Next, what we did is I'm asking you what's the derivative of x squared? At x equal to 1, 2, 3, 4, 5, 6, and so on. The same function everywhere. Then we realized we really don't want to do the same process for 5, 6, 7 times. Instead, we do it for 1 time. We call it the derivative function. It's exactly the same thing as we did before, except instead of putting a number, we put a variable x here. And when we finish, we will have a function with x inside. We call this the derivative function. We find all the derivatives once for all. Now you need 1, you plug in 1. Now you need 2, you need to plug in 2. You plug in whatever you want. That is great. Then we did some tricky questions. Just give you fx, try to draw f prime x. You can play the game forever. Okay, but I think we have done enough in class. And then the derivative function is done. Then we come to the third thing. From now on, I can ask you to find the derivative of sin x, the derivative of x cubed plus 1, the derivative of tangent times e to the x cosine x squared. I can give you all kinds of complicated things for you to find the derivative. That will be the whole chapter 3. Okay? But before we do that, before we go ahead and try to get the derivative, now we need to talk about, does the derivative exist? Is it always doable? Okay? The question here is, your derivative is defined as a limit. Right? It's basically a limit. Now, can a limit be does not exist? The answer is yes, it can. So when you find the limit, find the derivative using the limit, it's possible you get a number. That's your derivative. It's also possible that you have positive or negative infinity. Technically, we say this is no derivative, or your changing rate is infinity. And it's possible you have does not exist for a limit. So in 2 cases, we do not have derivative. So if I give you any random function, it's actually not differentiable. And then you go ahead and do it, you waste your time. Okay? Our job now is just give you a quick thing to check. Is this thing worth doing? Is it even worth storing the time to do it? Because maybe it's not differentiable at all. So let's talk about differentiability. How do we check if a function has a derivative somewhere? Okay. This is the fact. We can't prove it, but I can tell you. If a function is differentiable, then it is continuous. Okay. That means differentiability implies continuity. That's great. Okay. Then you realize, well, that's not the direction we want, because it's very easy for us to check if something is continuous. What we really want is, if we know some function is continuous, what can we say about differentiability? We want the other direction. Sounds good? Okay. Now here's the problem. If this is true, differentiability implies continuity. Is there a guarantee that continuity is going to imply differentiability? The answer is no. You switch the order, the conclusion may fail. Sounds good? But then, if you learned a little bit logic, at least I give you something which is guaranteed to be true. That is the reverse, and then you put a negation on it. So this one implies not continuous. Implies not differentiable. This comes from a fact from elementary logic. That there is quite simple. If A then B implies if not B, then not A. Has any of you done this before? Like a little bit logic before? If not, this is something really interesting to know. That help you to, I don't know, argue with people. For example, if I have the money, I would have bought you the car. Therefore, if I didn't buy the car, that means I didn't have the money. Right? Did you realize I reversed the order? Okay. I also put a negation on it. And can you see that these two sentences basically imply the same truth? Let me say it again. If I don't have the money, I have the money, I would buy the car. If I didn't buy the car, that means I didn't have the money. Because if I had it, I would have bought it. Okay, so that's simple logic. So differentiable implies continuous. Then if not continuous, not differentiable. Same thing. Reverse the order, put a negation. Now you have a function here. How do you check if it's differentiable? You check if it's continuous first. If it's not continuous, you can say not differentiable. I feel like everybody is sleepy. Come on, guys. This is the, I don't know, which week? Are we in week 4, week 3? This is going to go on for another, I don't know, another 3 times more. You better cheer up. You know, and I know 11 o'clock is a hard time, but yeah, you got to cheer up. I don't mind if you have to actually, you know, stand up, walk around, or even listen to some music just to cheer yourself up. Just don't fall asleep, okay? Try your best. Okay. Yeah, man, I wish I'm in the classroom. Okay. By the way, if I fall asleep, just wake me up. You don't have to raise your hand. I won't be able to read it. Okay. Don't just take a picture or just, you know, record it and put it on Facebook and say, hey, look, the professor sucks. Just don't do that. Okay. Help me a little bit. All right. Something continuous. We can't say it's differentiable, but if it's not, we can say it's not differentiable. Great. But that also means if it is continuous, we're still not sure. Then you say, wait a second, continuous means nothing is nice, right? But you are saying like, even if it's nice, you cannot find the derivative or changing rate. Then you need to think about question. Can you think of a function which is continuous, but not differentiable? Can you? Aaron, what do you have?
So I would say that it's possible because arctangent, it doesn't, I suppose that's not a function.
You mean tangent or arctangent?
What was that?
You mean arctangent or tangent?
Arctangent.
Arctangent is something like this. Yeah. I would argue this one is smooth enough, it's continuous. Meanwhile, it seems like it have derivative everywhere. Right? Yeah. Adam.
Would like the sine of the sine function that we did, I was like it's like,
oh, you are
oscillating. Yeah, like I don't remember the exact.
That's something like this.
Where you can't tell what's going on in the middle.
But here's the problem. This one is not continuous.
Oh, it's not continuous, yeah.
It's not continuous because you don't have a function there and you don't have a limit there. So, no. Yeah. You need something a little bit nicer than this, but not so nice. So you still don't know the changing rate. Can you think about something that just keep going, but somehow just by looking at what happens on the left and right, you can't tell if it's increasing or decreasing? What about something like this, which is a sharp turn? Number one, is it continuous? The answer is yes, it's continuous. Now I'm going to ask you, what's the changing rate here? On the left, if I ask you to make a guess, what do you think? It's going to be increasing, maybe +1. That's my changing rate. On the right, what are you going to guess? I'm going to say it's decreasing, maybe it's -1. Good so far? So looking from the left, looking from the right, you have different changing rate. That basically means if you use the limit, you have a left limit and a right limit, and they don't agree on each other. Therefore, the limit does not exist. Therefore, there is no derivatives. Kind of makes sense here? If I ask you to draw the derivative of this thing, how are you going to draw? Well, on the left, it's this. Right? On the right, definitely it's this. Okay? But what's the derivative at 0? Do you, let me put circle here. But which one do you think I should put a dot there? At this point, is it increasing or decreasing? Can you see left and the right doesn't agree on each other? And you should treat them equally without taking preference. You don't say the right is more important than the left, or vice versa, right? Therefore, it's impossible for me to put which one is dot. Then this part is empty. No derivative at x equal to 0. So here's the example. It's continuous at here, but not differentiable. Good so far? Okay. So in our class, we are going to look for something. fx coming in, we need to rule out 2 cases. Number 1, we need to make sure it's not continuous. Oh, sorry. It's continuous. Okay. Then second, even if it is continuous, we need to make sure there is no sharp corner. Otherwise, your derivative jump. Your left and right derivative does not agree on each other. If both are checked, we say it's differentiable. Okay. But that only works in our class. In general, this is wrong. But in our class, if you check the 2 things, you don't have them, you can say it's differentiable. Sounds good? That means you have a third case, which is not a corner. It's continuous, but still not differentiable. So you may start to wonder, continuous is like this, right? Which means you are smooth. Differentiable also means you are smooth. Still okay? At the beginning, we tend to say, hey, basically you guys are the same thing, but then you say you guys are not the same thing. At least in this case, you guys are not the same thing. Why is it's continuous but not differentiable? Still okay? But then what you say is, even if that happened, you guys are not the same thing, but you guys are almost the same thing. Right? It's just like for some bad cases. It may happen, but it only happens for 1 point or maybe 3 points. But after that, other than that, everywhere else, continuous and differentiability are still roughly the same. Make sense so far? Okay. So the key difficulty here is try to tell people how different are continuous and the differentiables are. Are they almost the same concept except for some rare cases? Okay. Or are they fundamentally different? They are way different from each other. Do you see the question here? For now, your feeling should be they're almost the same, except for some bad cases. Right? Then, fundamental question here comes. Can you imagine there is a function fx satisfying the following 2 things? Number 1, It's continuous everywhere. Number 2, it's differentiable nowhere. If such function exists, then differentiability and the continuity are two totally different things. Good so far? If such function does not exist, then they're almost the same thing except for some bad points. That's it. Does the logic make sense here? The question becomes, do you believe such function exists? Of course, in mathematics, you don't say you believe. You say, here's the formula of that function. Please take a look. Okay. What do you think? Yes? Possible? Or no? Anton?
Oh, never mind. I thought we were raising opinions. Sorry.
Yeah, opinions is yes or no, not you click raise your hand. Okay, try to take a vote. Do you believe so? Use your common sense. Can you think about something that is continuous everywhere? It's smooth. But somehow you cannot tell the changing rate. You cannot tell where it's going next. We have 2, 1, 3, 1. Two, 6, 2, 7, 3. Okay. Let's hear people who says no. 8, 4. Okay, we got 2 against 1. Roughly the ratio. Let's say let's call a person who said no. Bryony, you said no.
Yeah, I said no because, can you hear me okay?
Yep.
Okay, yeah, I said no because I think that if it's continuous, it wouldn't be able to be continuous everywhere without running into itself, I guess you could say. If that makes sense. If you can't like predict where it's gonna go, I feel like it would have to run into itself again, which like would disrupt its continuity.
So from the beginning, it's not even a function anymore, right? It's just like, okay, you're smooth, but then you run into yourself. And that's at this point, I cannot tell where this one's going because I have 2 possible directions, right? But then you're not even a function.
Right.
So this case cannot happen. Therefore, you kind of think this is the only case this may happen, but it doesn't happen. Therefore, seems like they are the same thing. Great. Okay, people who answered yes. Anton, since I caught you just now, why do you think it's yes?
The one thing that came to my mind is when you talked about earlier in the semester with that one function where rational numbers would be 1 and irrational numbers would be 0.
That's good, but my question becomes, is this one continuous?
I thought we concluded that it is continuous.
We actually didn't say.
Oh, we didn't conclude?
We just said, actually the answer should be not continuous. And the reason I can show you why. Okay? Basically, you just pick any number, right? And on the left, on the right, you try to guess what's the limit here. Because I already know the limit here is 1. The function value here is 1. Now your problem becomes, no matter how small you take the interval, there will always be some point here. There will always be some points here. Still okay?
Yeah.
Therefore, you cannot tell where the limit is. For the limit to be 1, you need all the points to stay here. Nothing here. Then you can predict. So that is actually not continuous.
All right.
Do you want to change your answer?
Yeah.
Then no? Okay. Adam Milk.
I don't necessarily have. I was kind of thinking back to something similar to that. I mean,
But then you realize
or-
it's not continuous, right? So
Yeah.
as long, so from here you guys can see that if it's continuous, you already require that thing to be nice, kind of, right? And if you're nice, it seems like you can predict where it is going, at least for a small time. Okay, very good. The answer is yes. And that is not an elementary function. That's not something we common sense can think of. That's something by construction called Weierstrass function. And I can give you a taste of this function look like. Chrome. Can you guys see my screen? The share to my laptop screen?
Let me see. Yeah.
Okay. What about now? All right. The function look like this. Okay. Now I'm going to show you a video to show you the detail of this. Weierstrass function. Let's see an animation here. Okay. Number one, the formula of the function is given at the left corner. It's Wxn. So this is the Weierstrass function for a fixed n. N can be 100. You just add 100 functions together. Every single function from here you can see it's cosine a to the n pi x. So every single function is continuous. You add them all together, it's still continuous. Good so far? What I am showing here is an animation, how this function is going to change when you add more and more terms. Sadly, the computer has to end somewhere. So maybe they did 1,000 terms. Still okay? It's still continuous. You have 1,000 terms. But the real Weierstrass function actually let n goes to infinity. So you have to add infinitely many functions together in order to get the last one. So what I am showing here is just a baby version. You need to keep doing it. Sounds good? Let's see how the function become not differentiable. Even though it's always continuous, no matter how many terms you add to it. Okay, let's stop at the last part. Do you roughly get an idea what this function looks like? Okay, so what you have is something oscillating like crazy. But it oscillates so much such that it destroys the differentiability of the function. Meanwhile, it doesn't oscillate that much such that we receive something similar to what we had before. You oscillate too much, you destroy the continuity. Good so far? Then this one shows you there is plenty of room between continuity and differentiability. And we kind of know where the boundaries are. Below that, you are not differentiable. And keep going. Below that, you are not continuous anymore. Okay. But if you can be above continuity, but below differentiability, and there is plenty of room there. Still okay? So that's what we're trying to say here. That's Weierstrass function. This guy is a famous I think he's a high school teacher actually, but he gives lectures in at universities. He actually solved a really, really hard problem by doing the construction here, which is actually the second crisis of mathematics. Have you guys heard about mathematical crises before? The 3 mathematical crises? Okay. Remind me later if you want to hear about it. It's pretty fun. But let's just focus on this now. So basically, let's go back to the classic question. Well, this one, destroy all your common sense. Okay, just by common sense, continuous should be differentiable. This one tells you no, there are things beyond your imagination, which you cannot tell by experiences. And then this is actually tied to the second mathematics crisis, which we actually have already mentioned before. Because Isaac Newton invented the whole thing of calculus, and people think, wow, it's great. And it's also easy to compute. Even us, like we're not big mathematicians, we can compute the limit, and we can compute the derivative. Moreover, people checked it. It matches with the experiment. So there are all evidence showing that this is true. And everybody in our class know now this is 2x. That's how we show the derivative of x squared is 2x. Please check the work. I will close the window. Man, never raise a kid. Okay. You guys follow the calculation? That's easy, right? Now, back to the question again. Is h 0? We did this at the beginning. If h is 0, how are you supposed to divide something which is not positive or negative? It's 0. You cannot do that, right? What if h is not 0? If h does not equal to 0, 2x plus h is 2x plus h. It is not 2x. Make sense here? So people actually attacked Newton. That is in physics, your idea of velocity, average velocity becomes instantaneous velocity when your interval becomes 0. That clearly makes sense, right? Secant line becomes tangent line. That clearly makes sense. But then people start to ask, like, how much can you trust your sense? Because clearly your sense has an elementary mistake in mathematics. Do you want to say, like, mathematics is a joke? Because your sense works that way? Do you see the contradiction here? It took people 200 years to actually figure out finally what is the right language to define limits, other than it feels like it, other than my experiences told me so, or other than, yeah, it makes sense. You need some mathematical rigors here. Still okay? Now again, I want to mention, what's that rigorous to solve this problem? So there's no more confusion anymore. That is actually the epsilon delta language. Let's turn something subjective into something objective. Let's try to quantify what you mean by close enough. Let's try to quantify what you mean by as big as you want. Sounds good? Okay, that's the whole point of 2.4. Sadly, we cannot touch it, but if you are ever interested in pushing further in mathematics, you will see this a lot because you're talking about something hard and tricky and against your common sense here. You have to trust this. Of course, then people ask, is mathematics true? Did we invent mathematics? Is it an artifact or is it actually the truth of the nature? I won't give you the answer. You think about it. Okay, what do you trust? Either way, this is settled. For our class, just check the two things. Where is it? Yeah. If it's continuous and there's no sharp corner, in our class, we conclude it's differentiable. Even though we now know, in general, we cannot say a thing, even if you know these two. Okay? But for our class, we're good. All right. Finally, the last thing. Oh, before we move on, Any questions regarding to the stuff we had just had? Of course, I won't test it. Okay, this is just for, yeah, Aaron.
This isn't about this is what you wanted me to remind you about Friday. Do you want to do
Oh,
about that later?
yeah. I hope everybody received my email, but if you, in case you haven't, I just say it. Friday we won't have class. I need to drive to Winona for some medical issue. Yep. Thanks, Aaron, for doing that. Yep. Who feel excited after hearing about things like this? Like something hard to talk about. Do you feel intrigued? Do you want to hear more? Okay, we have calculus 2 and 3 waiting for you. And after that, do real analysis. It's a fun class. Through doing that, you will eventually, try to approach the crown of human intelligence. That is something totally you cannot get from everyday experiences. Okay, it's purely in your mind. You cannot even verify it. You cannot see it. You cannot hear it. You can just trust your mind. Okay, so if you're interested, try to push a little bit further. You will hear more in real analysis. Okay, last thing, differential operator, or let's just say notation. Okay. The idea here is quite simple. This means derivative. Okay. But now we want to invent another notation to denote the same thing. We call it dy over dx. And they are the same. Then, of course, why bother, right? Did you hate f prime? No. Each of them has some simplicities. This one looks nice. It's easy. But now I want to show you why this one is great in some cases. Number one, this one is great because it gives you a ratio. This one reminds you, how did you get your changing rate again? Well, technically, you took your change in your y divided by your change in your x. We call this delta, which indicate for change. Delta y, delta x. Okay, then when you let delta x goes to 0, you cannot use the same notation anymore. Then you use a variation, which is dy over dx, which come from exactly the same notation, but just change it because you let everything to be extremely small. Sounds good? That's more intuitive because you have a ratio or you have a slope here. Second interesting thing here is later, for some circumstance, we actually will be able to do computations directly at this level, which means if we have something here, which equals dy over dx, I can even do this by multiplying dx on the other side. Okay, this is certainly something you cannot do with this notation because you only have one thing. You don't even have a fraction there. So that's why this is good. Second advantage come from here. What's the derivative of r squared? It's 2r, right? If r is a variable. But we have seen this. If we use algebraic representation, sometimes r means a constant. So looking at this is nothing but looking at 2 squared prime. That is 4. Does 4 change? Not really. Therefore, this one is 0. If you think r is a constant. Still okay? Can you see that with this notation? We actually don't know which case we're dealing with. Therefore, we get confused. Okay. Now check the new notation. If I do this, that means I want to see the changing rate of r squared with respect to r. Therefore, r is a variable. This is 2r. Okay. But if I use the dr squared over dx, I'm thinking about the changing rate of this one with respect to x. X should be the variable. Therefore, r is a constant. That is going to be 0. So taking a letter here, differentiate these two cases, which cannot be differentiated before. That's another advantage of this notation. Sounds good? Okay. Later in your life, you will do calculus 3. In that case, you may have some function which depends on 2 variables, which is very possible. For example, think about the temperature, right? Number 1, the temperature depends on time. As time changes, your temperature change. Number 2, even for the same time, the temperature changes in the room. It changes by location. Make sense so far? So can you see we have 2 changing rate? The first one is I fix the location. I let time pass by. How fast is my cooling down? How fast is my warming up? Second, for the same time, I fix the time. But if I change the location, for example, I move to the right of my room, how fast is this one increasing or decreasing in terms of temperature? Can you see we have 2 or more derivatives there? Depending on which variable you're talking about. Okay, that's why this become handy again, because you know which variable you're talking about. Cool. Finally, just the last one. High order derivatives. I know you guys are tired. I'm just going to write it down. You read it yourself. I just tell you what you need to know. Okay, I won't talk about it. Sometimes we want to do nth order derivative. For example, second order derivative, seventh order derivative. We use the notation n, or we use the notation n here. Okay, this basically means take the derivative for n times. For example, this one is 2x. This one's second order derivative is going to be 2x first, do the derivative again. This one to the third derivative is going to be do it for once, do it for twice, and then do it for 3 times, which is 0. Okay? Usually in our class, we stop after second order. The reason is because when you have location, then y prime give you velocity, which is the changing rate of your distance. Second order derivative give you the changing rate of your first order derivative. That gives you the changing rate of your velocity. Do you know what that thing is called? Acceleration. Now, going from Newton's law, you know you need to push things to the second order very often. Okay, that's it. That's all for today. By the way, does anybody know the name of the changing rate of the acceleration? Google it. We do have a name. Beyond that, we don't bother to name them. Okay. Class is over. Take some good sleep. Hopefully tomorrow you have more energy.